In our last lecture, we explored the decimal, binary, and hexadecimal systems, the foundations of how computers and PLCs represent numbers. Today, we shift focus from number systems to coding systems that serve special purposes in digital electronics. Why do we need these codes? Because raw binary isn't always the most efficient or reliable way to represent certain kinds of information. For example, when displaying numbers on a digital readout, it's easier to use a code that aligns closely with decimal digits. Likewise, when working with mechanical devices like rotary encoders, we need a system that prevents errors as numbers change. By the end of this lecture, you'll be able to define BCD and Gray code, compare between decimal, BCD, and Gray code, explain why these codes are used in PLCs and industrial systems. This lecture builds on what we learned about number systems, and it will show how engineers use coding strategies to make digital systems more practical, more reliable, and less error-prone in real-world applications. First, let's take a look at binary-coded decimal. The binary-coded decimal, or BCD system, is a method of representing decimal digits in binary form. Instead of converting an entire decimal number into one long binary string, each individual decimal digit is replaced by its own 4-bit binary equivalent. For example, the decimal digit 5 becomes 0101, while the digit 9 becomes 1001. This approach makes BCD very easy to read because the decimal digits remain clear and distinct inside the binary code. Let's look at an example with the decimal number 7863. In BCD, the digit 7 becomes 0111, the digit 8 becomes 1000, the digit 6 becomes 0110, and the digit 3 becomes 0011. Putting these groups together, the decimal number 7863 is represented in BCD as 0111, 1000, 01100, 011. Notice how each decimal digit is simply mapped to its 4-bit binary code, rather than converting the entire number as one continuous binary value. This makes BCD particularly useful for digital displays, counters, and timers, where numbers must be displayed in decimal form for humans to easily understand. It's also important to distinguish BCD from pure binary. For example, the decimal number 49 in binary is 11000012, but if we write it in BCD, the 4 becomes 0100 and the 9 becomes 1001, giving 0100 1001 BCD. To make the difference clear, we use a subscript to indicate the system. Binary represents the whole number as a continuous string of bits, while BCD keeps each decimal digit separate. The trade-off is that BCD is less efficient than binary. It requires more storage, but the advantage is its readability and its ease of conversion back to decimal. A practical example of BCD in action is the thumb wheel switch. This input device allows an operator to select a decimal digit, which is then automatically converted into BCD for the PLC to read. The input module connected to the thumb wheel has one line for each bit's weighted value: 1s, 2s, 4s, and 8s. If the user selects the digit 8, the switch outputs 1000 in BCD, with only the 8th bit active. This shows how BCD serves as a bridge between the way humans naturally work with decimal numbers and the way digital systems process data. Thumb wheel switches are commonly used in industrial systems for entering set points, machine codes, or parameters in a form that both the operator and the PLC can handle easily. The Gray code is another way of representing numbers in binary, but it works differently from the standard binary system. In Gray code, the numbers are arranged so that as you move from one value to the next, only a single bit changes. This property makes it unique and very useful in certain applications. Unlike pure binary, where several bits might change at the same time, Gray code avoids those simultaneous changes. This reduces the chance of errors when signals are read by a circuit. One thing to note is that Gray code does not assign fixed weights to bit positions the way binary does. This means it isn't ideal for arithmetic or counting operations, but it excels in applications where accuracy during transitions is critical. For example, when binary counters switch between numbers, multiple bits may flip at once, and if a circuit reads the value at the wrong instant, it may capture an incorrect result. Gray code avoids this problem by ensuring that only one bit changes at a time. This feature makes gray code particularly valuable in devices like encoders. Encoders are often attached to rotating shafts in machines, robots, and servo mechanisms to measure position. An optical encoder disk is marked with patterns that correspond to gray code values. As the disk rotates, sensors read these patterns and output a gray code signal. Since only one bit changes between positions, the chance of misreading the shaft's location is minimized. For example, a 4-bit gray code encoder can track 16 distinct positions. As the shaft rotates, the encoder outputs a sequence of gray code signals that represent the shaft's angular position. Because of the 1-bit change rule, the system is less likely to register errors when the shaft is moving quickly or when the sensors are not perfectly aligned. In summary, gray code is not designed for arithmetic, but for reliability in reading transitions. It is widely used in industrial systems to ensure accurate position, sensing, and motion control. That's why you'll often find gray code in optical encoders, robotics, CNC machine tools, and servo systems. Its ability to minimize errors makes it an essential code for real-world automation and control. In this lecture, we explored two specialized numbering systems that extend beyond standard decimal, binary and hexadecimal. First, we looked at binary coded decimal, BCD, which represents each decimal digit with its own 4-bit binary equivalent. Next, we studied gray code, a system where only one bit changes at a time as numbers progress. Together, BCD and gray code highlight how different coding systems are designed to solve specific problems in digital electronics and industrial automation. In the next chapter, we introduce the fundamental concepts of digital logic that form the foundation of PLC programming.